Hello, and welcome to Internuclear Distance Graphs for Intermolecular Forces. Now, we've seen these before when we were learning about intramolecular covalent bonds, so the intra, not IMFs, and we were comparing the difference between triple, double, and single bonds, and the difference between their bond length and strength, and that's what caused the shift. This is going to be a little different because it's not within a molecule, but it's between, usually in this case, ions. So it's an IMF. So obviously there's going to be a greater distance because you don't have any orbitals overlapping. So I'm going to go ahead and sketch it out for NaCl. Okay, so I've drawn here an ionic lattice. So that is this image up here to the left, if we remember. And this would be in 3D, except for I've only drawn it in 2D. And we see here the attraction between the cation, Na+, and Cl-. We remember that Na+ is generally the cation is going to be smaller because it's lost electrons, and it's pulling in those shells of electrons that are remaining. And anions generally will get bigger because they're gaining an electron, and you have lower effective nuclear charge holding on to those shells. And it'll alternate Na+, Cl-, Na+, Cl-, and it'll do this in a 3D fashion. I've only drawn it 2D here. So internuclear distance here is not going to be the bond length, but it's the distance between the IMFs. So if we take a look right here, it would basically be the distance between the center of the Na and the center of the Cl. So it would be this distance that you're measuring right here. Okay, so that would be the distance. Now this should be consistent. So between these two, it should be the same as these two and these two and these two and these two, because it's going to be fairly uniform. Okay, so I'm following all these lines. Each one of these would be an internuclear distance that you're measuring. And I'm going to erase this. Okay. All right, so the IMF that's present here, we know is the ion-ion IMF. Okay, so within ionic compounds, this is an ionic compound. So the internuclear distance graph for this, it starts out the same as when we learned it for intra. The two ions are starting far apart, so they're not quite feeling an attraction. There's an attraction there, but it's not quite strong enough to completely pull them together. So as you bring them closer together, and I want you to go back and remember the magnet activity we did, and as you held those magnets where they weren't touching each other, but they were getting closer, you could really feel that attractive force. So it's really important to remember that as we go down this way, as we're moving in this direction, right? So as we go this way, before we get to this point, with some little dots, we should be feeling an attraction. Okay? When we get to this point, this is where you're releasing the lattice energy, and this is where it is balanced and stable. So this is where it's going to stay, and that would correspond to the distance that we find right here. Okay. Now, if you try to push them any harder together, you would end up getting a repulsion because they're just too close. And that happens with the magnets as well. If you try to get the magnets too close, they wouldn't go any closer together without you forcing them. And even then it was very difficult. Okay. So the big difference here, this is still going to be where the IMF forms. It's an IMF here, not an intramolecular bond. Obviously it's going to be a much larger distance because you're not getting the atoms as close together. They're near each other, but not overlapping like they are with an intramolecular bond. The other difference is that you need to be able to describe the shifts down and then the left-right shift a little bit differently because you're not dealing with single, double, and triple bonds. Instead, you're dealing with the different strengths of ion-ion interactions. So ion-ion interactions are going to be governed by Coulombic, we've heard that a lot this year, Coulombic attractions, which is a force. So Q1 and Q2 are charges, and D squared is going to be distance. So what influences the charges here is the size of the charges on the ions, and the distance is going to be dependent on the size of the ions. I've put a big star here because remember, we always check the size of the charges when comparing before we look at the size of the ions. We always look at the size of the charge. So, for example, if we're comparing NaCl versus MgS, the first thing you look at is the charges. So this would be Na is +1, Cl is -1, Mg is +2, and S is -2. Because these have different charges, we look at that and focus on that, okay? So because this has greater charges, both positive and negative, this is going to have a stronger Coulombic attraction, okay? So you have increased Coulombic attraction, which means you have a stronger ion-ion IMF, which would mean that this would take more energy if you wanted to break this, like if you wanted to dissolve it or if you wanted to melt the salt, etc. It's going to take more energy to break this lattice up. So let's see what this looks like in terms of the graph. So I have here, I just redrew the one for NaCl. These, I'm not putting any number values on them. We're just estimating. So we'll kind of come over here. This would be the bond energy, and this value here would be the bond distance, right, along the x-axis. And if we remember, lattice energies, just like bond energies, are going to be negative because when you form them, they release energy, which is a negative value. If you were going to break it, it would be the same number, but just positive. So if you wanted to know, does something have enough energy to break that lattice, and you were calculating it, you would just use the value that you would read here, but make it positive. So how would this look then for MgS? And I'm going to change colors so we can see here. Well, we said before this has stronger Coulombic attractions because it has greater charge in both the cation and the anion. So that means that we need to shift it down because it's more energy. And they're also going to be closer together because if they have a higher charge, they're going to be more attracted to one another, and that's going to pull them closer. So closer together and higher charge, it's going to mean it's going to go down here, more energy and closer together. And I made the trough so it's a little bit easier to follow and something that looks like that. Okay, so we notice here that MgS has a shift to the left. And that is because they're closer, and it has a shift down because it is more energy. When we read graphs in chemistry, it's really important that you're noticing both the X and the Y, not one or the other. You have to look at both and how they're impacted. So let's take a look at this in another example. Okay, so let's take a look at the example of LiF versus NaCl. So again, the first thing we always check for is charge. So Li is +1, F is -1, Na is +1, Cl is -1. There's no change there. So now we need to go to size. LiF, both Li is going to be, these are both going to be smaller ions as they both have one less shell. So Li has one less shell than Na, and Cl has, or F has one less shell than Cl. So if these are smaller, that is also going to make for a stronger ion or ionic IMF. Okay, well, if it's stronger, that means it's going to take more energy. If we wanted to break it, it's also going to release more energy when it's formed. So we know that's going to be a shift down. We also know that since these are smaller, they're going to be closer together. So again, we should see a shift down and to the left. Make something that looks like this. Okay, really we're focused mostly on this. Okay, and then we're also focused on the fact that before this trough, anything to the right of it, so everything from here over is an attraction. At that point, it is balanced. Anything from here over is going to be a repulsion. And that's why the IMF keeps the distance and the lattice structure stays intact in that perfect uniformity. Okay, thank you for listening.